Welcome back to the RadSound Radiology Physics Series. Today we're going to take a pretty incredible journey. We're going to follow a single X-ray photon, all the way from the moment it's created to the second it helps form a diagnostic image. It's really the story of how pure, invisible energy becomes a picture that can literally save a life.
You know, when you think about it, every single X-ray we see is a complex story. It's a narrative written with a form of energy we can't even see. And it's a story that reveals the secrets hidden inside the human body. Everything from a tiny fracture to a serious life-threatening condition. So, the big question is, how does that story get written? How do we actually take this invisible energy and turn it into a clear, detailed picture that a doctor can use? Well, that's exactly what we're going to break down in this explainer. And it all starts with one fundamental idea.
Everything, and I mean everything, in this process comes down to one word: contrast. It's just the difference you can see between two things right next to each other. Without contrast, an image is just a gray blob. So every single step we're about to walk through is designed to do one of three things: create contrast, protect it, and then optimize it.
Okay, so our story really begins the second that X-ray beam hits the patient. This is the moment where the raw information, the actual blueprint for our final image, is first created. It's like a shadow play at the atomic level. The key process here has a bit of a technical name: differential attenuation, but it's really a simple idea. As X-rays shoot through the body, some get absorbed, some get scattered, and some just pass right on through. And the crucial part is that different tissues, like bone, muscle, and air, do this in very different ways. That's what creates the initial pattern.
And this table really shows you just how dramatic those differences are. I mean, look at bone. It absorbs a whopping 80% of the photons that hit it. Now compare that to the lung, which is mostly air. It lets 90% of them sail right through. This incredible difference is exactly why we can see a bright white rib against the dark lung tissue behind it. This right here is the birth of image contrast.
So all those photons that actually make it through the patient are what we call the remnant beam. You can think of it as an invisible message, a pattern of energy that carries all the useful anatomical information. But, and this is a really important but, it also carries a whole lot of noise.
And this slide breaks down those two parts of the message perfectly. On one side, you have the pure signal. These are the primary photons that traveled in a straight line, carrying clear information. On the other side, you've got the noise. This comes from scattered photons that have bounced around inside the body like pinballs. They end up hitting the detector in the wrong spot, adding this layer of fog that just degrades our beautiful signal.
As Dr. Jafar so perfectly puts it, scatter is the enemy of contrast. It's basically the main villain in our story. Anytime you're imaging a thick body part, say an abdomen or a pelvis, the biggest challenge you face as a technologist is winning the battle against that scatter.
All right, so we've got our invisible message, the remnant beam. Now what? The next big challenge is to actually capture that message and translate it into something we can see, a visible image made up of pixels on a screen. Now, there's another kind of noise we have to deal with, and it's called quantum model. Because photons are these tiny individual particles that arrive at the detector in a totally random pattern. If you don't use enough of them, the image looks grainy and noisy. It's just a statistical thing. And this brings up the fundamental trade-off between image quality and radiation dose. So here's what that looks like. This image was made with a relatively low number of photons. See that grainy, almost salt and pepper texture? That's quantum model, and it makes it really hard to see fine details clearly. And now, look at the difference when we use 10 times more photons. The image is dramatically smoother, it's clearer. We've basically drowned out that random statistical noise with a much stronger signal. But this brings us to that crucial point again. More photons means less noise, but it also means a higher dose to the patient. It's always a balance. And this is where the detector itself becomes so important. See, not all detectors are created equal. We measure how good they are with something called detective quantum efficiency, or DQE. The easiest way to think about it is like a batting average for the detector. A high DQE detector is super efficient. It makes the most of every single photon it catches, giving us a really crisp, clear image at a much lower dose. And that's a huge win for both diagnosis and patient safety.
And you can really see the massive technological leap right here on this chart. The old film screen systems, they were only about 20% efficient. That means they were wasting 4 out of every 5 photons. Modern direct radiography, or DR systems, can hit 60% efficiency or even higher.
This is the main reason why modern tech lets us slash the radiation dose while actually getting better images. It's been a total revolution for patient safety.
Okay, so we've created the blueprint with differential attenuation, and we've decoded it with our detector. Now, let's put it all together and talk about what makes a truly great diagnostic quality image.
You can really think of it as this triad of image quality. First, we need sharp detail, which we call spatial resolution, so we can see tiny little things like fracture lines. Second, we need good contrast resolution, which lets us tell the difference between similar types of tissue. And finally, we need an acceptable low level of noise, so the radiologist can make a confident diagnosis without any distractions.
And the way we balance these three pillars changes with every single exam. For something like a hand X-ray, we'll use a low-energy beam. This maximizes the contrast and lets us see those small bones with incredible clarity. But for a chest X-ray, we actually do the opposite. We intentionally use a high-energy beam. Now, this lowers the overall contrast, but it's a necessary trade-off because it allows us to see the delicate lung tissue through the ribs. It's a perfect example of tailoring the physics to the clinical question you're trying to answer.
And all of this brings us to what is maybe the most important balancing act in all of radiology. That constant push and pull between getting a crystal clear picture and making sure the patient is safe. Everything we do in this field is governed by one guiding principle: ALARA, as low as reasonably achievable. The real art and science of radiography lies right here, in this challenge, using the absolute minimum number of photons you need to get a diagnostic answer, and not one single photon more.
But modern technology adds a really interesting twist to this challenge. This quote from Dr. Jafar just nails it. With old school film, if you used way too much dose, the film came out black and was ruined. It was honest about your mistake. Modern digital systems, though, are incredibly forgiving. They can automatically fix an overexposed image and make it look perfect. But that forgiveness, it's deceptive because it can completely hide the fact that the patient got way more radiation than they needed to.
What this means is that even though the technology is amazing, the responsibility on the radiographer, the person taking the image, has never been greater. It's truly an art form. It requires mastering the physics, choosing the absolute best technique for each and every patient, getting that diagnostic clarity, and above all else, upholding that promise of minimal dose.
And that really leads us with a final important question to think about. In this era of automated, almost perfect-looking images, how do we make sure that the expert human judgment behind every single exposure remains the most important part of the whole process? Because that balance of art and science, that's what makes this journey from photon to picture so amazing.